I am recording in case anyone's going to ask, and my voice is in it, and desktop audio is in recording. Let me just check. Yeah. Okay, perfect. So let's start now. Then let me make it just a list of things for today. So list of questions we will cover. Okay, so I have a Laplace solution, like solve a differential equation using Laplace. Solve a differential equation using Laplace question. But it's a good one, right? It's not just a simple one, right? And then I have also a convolution question. Okay, then I have Fourier questions. I actually have a couple. I don't know exactly how many I'm going to do. And then I have some polar stuff, polar questions, right? So hopefully that's a good list for today. That probably will take the 2 hours, especially that Fourier section. You know, it's just 1 point, but that will take a little bit of time. But yeah, okay, let's get started. So the first question I have is question 8.5.1 from the homework, and it looks like this. It's a pretty good one. So there it is. That's our question 1. So the question says we have y double prime plus y equals this piecewise function, and there's our initial conditions. Luckily, our initial conditions are 0 in this case, so that does make things a little bit easier, but the actual solving of this is a little tricky. So, did I start recording? Yeah, I did, good. So, first things first, we got to turn this piecewise function into a unit step function, like represent it using unit step functions. We could do it using just like the definition of Laplace, but that would be a little bit troublesome. So let's try it to do it just with a unit step function. So y double prime plus y equals, okay. And so now we got to figure out what this is here. How I like to think about it, I don't really use any of the formulas for this stuff. I like to think, okay, so it begins with 3. And then eventually we subtract 3. When do we subtract 3? Right? At pi. And that's how I like to think about it. It begins with 3. We then subtract 3. Right? And when do we do it? At pi is when we do it. And then we're lucky here that it's actually just 0 after. So if it was like another number, like x here, then I'd have to add, x. And when do I add x? I add x at pi as well. Right? But there is no x there, so it's just 0. So there's just nothing else to add. So hopefully that makes sense. If you have any questions about that, let me know.
Yeah, it's the part where you said minus 3. So yeah. Where's the part that they minus 3? And then that's where you get the second 3 from? I don't get that.
Well, think of it like this. Let's look at a little line like this. So this section is this is at t equals pi. So before t equals pi, what's this expression equal to? Well, it's going to be 3 minus, right? And remember, it's going to be 3 minus 3 minus 3 times 0, right? Because the unit step function is 0 before pi in this particular case. Does that make sense to you?
Oh, okay, yeah. So it's at the value of 3, and then after pi, then it drops down to 0.
3 minus 3 times 1, which is 0. Right?
Yeah. Okay.
After pi. And so that's how I like to think about it in terms of this instead of using formulas, because I think it makes more sense to think about it like this. I didn't need to make that whole axis there. There you go. Right. So does that make sense? I am recording. Someone asked me, am I recording? Yes, I'm recording. We're good. Yes, I'm using OBS to record. Not to Zoom is what we're using for this, but to record, yes, I'm using OBS. Okay, so now that I have this in my unit step function representation, now I can take the Laplace of it, right? So we're just going to take the Laplace of y double prime. I'll immediately distribute it over the addition, right? So then we have Laplace of y, right, equals Laplace of 3 minus 3 times Laplace of the unit step function t minus pi. Okay, so just use the linear property there. And then here we have, for the Laplace of y double prime, right, we have, it's just using the formula for the derivative there twice, right? So we just have s squared f of s, or I'll call it y of s, I guess, because it's the thing. It's just a little hard for me to write a capital Y. So no, it's still wrong. There we go, y of s. And then a bunch of initial conditions, but those initial conditions are 0, right? So it doesn't matter. Like, I don't have to include those. So then it's just plus y of s equals, so it's going to be 3 over s minus 3 times, and now we got to figure out what's the Laplace of the unit step function t minus pi, right? And so there's a couple ways we can do this. But I think the way, okay, so first of all, you can just do it from a table. I mean, you can just look up the table value of this. But another way to do this is by one of the translation theorems. So let me get that translation theorem up, and we can take a look at what it would be. So
sorry, just for that Laplace for that unit step, it's always going to be 1, right? Doesn't matter if it's like t minus whatever. It's always going to be 1.
Like, what do you mean 1? Like 1 in the front here, multiplying?
No. So like you see over here for your second line, you have 3 over s,
Yeah.
and then minus 3.
Yeah.
That's because the Laplace was equal to 1, right?
Oh, sorry. I'm not done writing. There's going to be something here. I'm not done writing.
Okay.
Yeah, not quite. So I'm still trying to figure out what that Laplace is. And so we can do it by the second translation theorem. Yes, second translation theorem, which states this, but then I'll show you in a second. So I have this, and then I have this. So there's the actual second translation theorem. But then there's a way to restate this, which there's a whole theorem about that, as this, which is a little bit more convenient for our sake right here, right? So what we're gonna say is that what we have here is the Laplace of 1 times u of t minus pi, right? So then, well, what we have essentially here is it's essentially this second part here, right? Which is Laplace of g of t u of t minus a, which is 1 u of t minus pi, is equal to, okay, and so now let's see what it's equal to. So right away here, I'm just going to factor out the y of s just to make our lives a little easier. So s squared plus 1 equals 3 over s, okay, minus 3 times, okay, and now what's in there? Well, it's going to be e, okay, here, e to the negative negative pi, yeah, e to the negative pi s, right? Just using this formula right here, right? E to the negative as, okay, so t minus a, e to the negative pi s. And now we need the Laplace of g of t plus a, but our function's just 1, right? So if g of t equals 1, g of t minus pi, or plus pi, right? Well, that's also 1, right? So it's still the Laplace of 1 there, right? So we can just continue on from here now. Okay, so this is just going to be, yeah, e to the negative pi, yeah, it is going to be, right? So y of s, now we're just going to have s squared plus 1 equals 3 over s minus 3 e to the negative pi s over s, because Laplace of 1 is 1 over s. Well, so someone asked, why is g of t plus pi equal to 1? Well, g of t is 1. So you see the output of the function, it doesn't depend on t, right? This function is just the constant function, right? It's just a flat horizontal line output of 1, right? So it doesn't matter if I'm like, it doesn't matter where I choose the output will always be 1, right? Remember, g of t is equal to 1. The whole function is equal to 1. Doesn't depend on t at all. So at t it'll be 1, at any particular input it'll be 1. So including t plus pi. Right? That's how we essentially deal with Laplace of the unit step function. It's just say that the function multiplying there, g of t, that's our g of t. Right? So I'll write that here. G of t equals 1. So g of t plus pi is also 1. Right? It's just like if f of x equals 3, then f of x plus 1 is also 3. The output's always 3. So hopefully that makes sense. Let me know if you need more explanation. I can. But okay, good. So now we just want to simplify this for y of s, right? So we can do that. So y of s equals, and now it's a common denominator here. So 3 minus 3e to the negative pi s over s times 1 over s squared plus 1. Okay. Then we have just a nice y of s equals 3 minus 3e to the negative pi s over s squared plus 1. Okay, and now we got to take the Laplace inverse of this, right? And so it is, how many questions have we done so far? This is the first question. This is the first one. So from here, sadly not 4, we're not that fast. We want to do, I mean, we probably want to do partial fractions, right? But we can't just do it right away because we have an exponential term in the top there. So what you want to do is you want to just separate out the numerator. So the numerator is in 2 parts here. So it's 3 over s squared plus 1 and then you have minus 3 e, well, I'll write it as minus 3e to the negative pi s over s times s squared plus 1. Right? Okay, so this we can do with partial fractions, and this we can actually also do with partial fractions. So the reason we can is, so first I'm just going to write this 3 over s squared plus 1 minus, and now you can just interpret this as e to the negative pi s times 3 over s squared plus 1. And we're lucky here because that's actually one of the translation theorems. Is it this one? No, I think it's the first one. Yeah, is it the first one? Laplace inverse of e to the... No, it's not one of the first ones. Yeah, because we're going to have... Yeah. So you see here, Laplace, we're taking the Laplace inverse of this, right? Because we want to get y. So e to the negative as, so we have, times f of s. Well, we just got to figure out what that is the Laplace of, right? And then we can just evaluate it like this, using this formula. So this is the formula that's going to help us deal with this, and then partial fractions is going to help us deal with this. So let's do partial fractions quickly. Do you guys think I should do it by hand or by calculator for the sake of time? Should I just type into a calculator? Obviously on the test you just do it by hand, but we've done a lot of practice of this, so I don't know if we need to. Let me know.
Yeah, you can just use a calculator. It's fine.
Just use a calculator? Okay, sounds good. Waste time doing that. So partial fractions of 3 over s squared plus 1. Well, sadly, I don't have an actual, I don't have a physical calculator that can do partial fractions, although I'd love that. I know of some calculators that can do it, but I don't personally have one. I wish. So, well, I'm just going to note here. So just note here that 3 over s squared plus 1 is equal to 3 over s minus 3s over s squared plus 1. Okay, so I can turn that into 3 over s. Whoops, that's not an s. 3 over s minus 3s over s squared plus 1. Okay, and then minus e to the negative pi s times that same thing, right? That's why I left them both as 3 over s squared plus 1, because they both have the same partial fraction. So 3s over s squared plus 1. Okay, so now we want the Laplace inverse, right? This is y of s. So we want to find y of t, really. So we take the Laplace inverse of both sides here. So this is going to be 3, right? That Laplace inverse of that is just 3. Minus, okay, and this is going to be, well, let me write it out fully, just so it's going to be 3 times the Laplace inverse of 1 over s, minus 3 times the Laplace inverse of s over s squared plus 1, right? Minus the Laplace inverse of e to the negative pi s times, and now, well, yeah, I'll just write it like this for now. 3 over s minus 3s over s squared plus 1. Okay, and so now we can start continuing. So this is just going to be, that Laplace inverse of that is 1, right? And then, that's right. Yeah, that is right. For a second, I was like, wait a second, that's not right. No, it is. And then this one is minus 3. Well, you can just, this is just from a table, essentially, to know this. This is just going to be cos t. I'm pretty sure. Let's check that. But I'm pretty sure it's cos t. I have it. I have a solution here, so I'll just check my solution quickly. But yeah, that sounds about right to me. And then from there, let me just see that I wrote cos t here. Cos t. Negative 3 cos t. Yeah, that's good. Then now from here we want to be able to deal with this Laplace inverse. Okay, so how we deal with it is again by these theorems. So let me just bring them down here again, right? These are very useful for this question. Okay, and so we note this formula right there. So e to the negative as f of s. So f of s is the Laplace of something. So I want to write this as the Laplace of something. So it's going to be, why am I changing colors? Let's not change colors. It's going to be Laplace inverse e to the negative pi s. And what I want to do is I want to write this as the Laplace of something. Well, it's the Laplace of 3 minus 3 cos t. We just saw that over here, right? We just saw that same thing over here. And now we have almost exactly the form, not just almost exactly, we have exactly the form. E to the negative as times the Laplace of something, right? Laplace of some function f of t. That's the function f of t. And then this is equal to now f of t minus a, right? So let's take a look at what that is. 3 minus 3 cos t, okay, minus, okay, and now this is equal to f of t minus a. So that was going to be f of t minus pi. So 3 minus 3 cos t minus pi, right? Times the unit step function. I think I forgot a 3. Did I mess up a... There's supposed to be a 3 in here. No, never mind. The 3's already there. Yes, never mind. I thought there was supposed to be a 3 out front, but it's already inside. And then times, I want to multiply this whole thing here, so I'll just use those brackets like that. I want to multiply this by the unit step function at t minus pi. I had a couple too many brackets there, but it's okay. So again, just following that formula right there. Hopefully that makes sense. Any questions, let me know. We can do this. Okay. So from here, we just do 3 minus 3 cos t, and you just write that as minus 3 minus 3 cos. I guess I'm not actually changing anything between these lines, am I? So just removing a bracket. That's all I'm doing. So there we go. U of t minus pi. Okay. And there you go. I mean, essentially that's it. And if you want to write that as a piecewise function, this is how I would do it. So it starts out, right? If we're defined from, since we're defined here, starting at 0, I'll again define starting at 0. So starting at 0, we're at 3 minus 3 cos t, right? Because this stuff isn't here yet. This stuff only activates at pi, right? So from t is between 0 and pi, right? That's what it is. And then at pi, this starts to activate. So it's going to be subtracting. It's going to be 3 minus 3, which is 0. Well, essentially, this is what it's going to be. It's going to be 3 minus 3 cos t minus 3 plus 3 cos t minus pi. Okay, that's essentially what it's going to be from t is greater than or equal to pi, right? But of course, the 3 and the minus 3 cancel. And so we have this left after. And there we go. There's your solution. That is y. Should just be clear. That is y. Y of t, obviously. Okay, that's the first question. Any questions about that question?
Yeah, the second translation theorem. So when you were first going, when you were pretty much trying to explain of some function, capital F of s, you chose for it to be 3 minus 3 cos t. Why is that?
Well,
Is that because
I didn't choose for that? I mean, that is what. So Laplace of this is this. The Laplace of this is this up here.
Okay.
So I didn't change anything. I just wrote it as wrote it as the Laplace of something instead of it already being.
It sounded like you just picked whatever, but that's not the case. Yeah,
that's not the case. Yeah, it's the Laplace of that. Yeah, should we make it piecewise? I'm not actually sure. Like it's equivalent, right? But that's like by that logic, like this is also equivalent to the answer. So yeah, maybe write it as piecewise. I guess I would write it as piecewise in the question, but I don't know. I don't know if they would take away marks if you didn't write it as piecewise. I'm not sure about that. So yeah. Okay, any questions? Again, if anybody's joining late, you can find my notes and link to everything after from that website right there. Okay, so there's our first question. Let's move on to question 2, unless anybody has any questions. And we can stop.
Would we be able to simplify that further?
Not quite, because this is t minus pi here. Oh, but t minus cos t minus pi is something. No, but then it's not going to be a cos.
Wouldn't it just be minus 3 cos t, and then we could do minus 6 cos t as our final answer?
Yeah, is cos... I'm very bad at these things. Is cos t minus pi equal to minus cos... equal to cos t? Is that true? I have it on my...
negative cos t.
Negative cos t?
Yeah, because if you think about it on like the graph, like it's high and ends low, right?
Let's think about it together. Okay, so there, move it. So this period here is 2 pi, right? This is the pi place. Okay, let me just. This period is 2 pi, and then we're gonna move it to the left by pi units. So this trough is gonna end up here, and then yes, it looks like it's gonna be negative cos t. Yeah. Okay, so that makes sense to me. So since that's true, good point. This is going to end up being y. Stick with the theme. Y equals, so it's 3 minus 3 cos t, 0 t, and then pi, and then yeah, so negative 3 cos t minus 3 cos t, right? Because that turns into minus cos. It would just be minus 6 cos t. All right, and we can just use that there. Perfect. Yep. Good point. Okay, so let's continue with the next question. Unless anyone has any notes to say, I appreciate it. Okay. If not, this is our next question. This is question 8.6.4c, I think. 8.6.4c. That sounds right to me, but it might not be right. 8.6.4c. Is that what it is? I'll just check here. 8.6.4c. That is correct. It is 8. I'll write it here. 8.6.4c. Okay, so the prompt of the question is just solve for y. That's the prompt of the question. Solve for y in this thing here, right? And so notice that we have a y of t over here, and we have a y of tau in this integral. Okay, and so we need to solve for y. Okay, so what you're supposed to notice is that this y of t, right, equals 1 plus 2, and this is going to be y convoluted with cos t, right? That's the convolution operation that we have there. Okay, so now that we've noticed that, we can take the Laplace of both sides. So again, we can't really solve for y just yet because we don't know how to really deal with convolution, except in one way. There's only one way we know how to deal with convolution, and that is by taking the Laplace of it, right? So I can turn this into y of s equals, and the Laplace of 1 is 1 over s, okay, plus 2, and then we need the Laplace of y convoluted with cos of t, right? Okay, so y of s equals, okay, 1 over s plus 2. And now how do we deal with convolution? Well, this is another theorem that we have in our notes here, or that we have from here. So it's called Convolution Theorem. It's very useful to deal with convolution, obviously. And so we have this, that the Laplace of the convolution is the product of the Laplaces of each thing individually. So this is equal to, I can just turn this into y of s Laplace of cos t. Okay, and at this point I can essentially solve for y of s, but I will turn that into the actual Laplace form. So y of s equals 1 over s plus 2y of s, and now Laplace of cos t is s over s squared plus 1, I think. Correct me if I'm wrong. I'm pretty sure that's right. And well, we'll see. Y equals 1 over s plus, and now, well, actually, I'm going to just isolate for y of s. So minus 2 y of s, s over s squared plus 1 equals 1 over s. And then we have y of s times 1 minus 2s over s squared plus 1 equals 1 over s. And we have y of s equals 1 over s times 1 over 1 minus 2s over s squared plus 1. I think this might be straying a little bit from my solutions. Let me just check my solution. I don't want to actually stray from it. No, that's fine. No, that's good. We're good. Same. I just forgot this 2 was there. Okay, so now I got to deal with that. That's a little bit messy. So what I'm going to do is I'm just going to write that as 1 over s times, and now I'm just going to say 1 over, just so we have a little bit clearer there. It's going to be s squared plus 1 over s squared plus 1 minus 2s over s squared plus 1. You know what, that's not more clear to write the fraction like that, so I'm just going to write it like that. So you see I just turned 1 into s squared plus 1 over s squared plus 1. So this is going to be 1 over s times 1 over s squared minus 2s plus 1 over s squared plus 1. Okay, so y of s therefore is equal to 1 over s times s squared plus 1 over s squared minus 2s plus 1. So I did that a little bit fast, so anybody, if you have any questions, let me know. But common denominated it and then flipped the fraction because we're doing 1 over. Okay, and now this is just a partial fractions thing to calculate, right? It's just going to be s squared plus 1 over s times s squared minus 2s plus 1, right? And from here, well, from here it's just it's just plugging into a calculator. So I'm going to plug it into a calculator as well. Obviously on the test, you can just do regular partial fractions at this point. So s squared plus 1, just for the sake of time, I'm just going to use the calculator. S squared, so s s squared minus 2s plus 1. So s squared plus 1, s squared minus 2s plus 1. Yeah. Okay, and so this is equal to 1 over s plus 2 over s minus 1 squared. Okay, that's nice. Looks like that factors nicely. So now we can just take the Laplace inverse of it to find y of t. So that's going to be, okay, well, 1 over s is just 1 plus 2. And now we need the Laplace inverse of 1 over s minus 1 squared, right? Okay, and so now how do we deal with this? So this essentially is going to be your first, not convolution theorem, your first translation theorem, which looks like this. Let me show you. First translation theorem. Sometimes I call them translation theorems. I don't actually remember which one's the right word. So one of the two. But anyways, I'm sure you understand what I mean. So we're going to do this. We need the Laplace inverse. We're doing the Laplace inverse of f of s minus a, right? Well, this is very close, right? This is very close to the Laplace inverse of 1 over s squared, right? It's just that we have a minus a in there. So how usually this is written, although I agree if some people are confused by this notation, is it's written like this, s minus 1, right? So a little bit weird, like that's not actually very helpful to write it like this. So if you're confused by this, you can just jump to using the formula. I think it's just better to just use the formula. But essentially this is just saying that, you do this Laplace inverse, but also remember that you're evaluating the Laplace inverse at s minus 1. You're not actually doing it at s. And that just reminds you to do this term here. There's no actual math that's really happening with this notation. It's really just a reminder that you are not exactly, it's not exactly Laplace inverse of 1 over s squared. It's Laplace inverse of 1 over s squared, but you've translated it to s minus 1. Sorry, it should be equal. So y of t equals 1 plus 2. And now what's this? Well, it's going to be e. So f of s minus a. So f of s minus 1 is going to be e to the t. And then f of t, well, what's Laplace inverse of 1 over s squared? That's just t. And just a little bit nicer way to call it 2 e to the t. And then I'm just going to write this as 1 plus 2 t e to the t. It's just a little bit of a nicer way to write it. And there's your solution. There's y. Y of t equals 1 plus 2 t e to the t. It's your final solution. I like putting it in box. Can't I do this question by evaluating the integral at the start? Well, evaluating the integral, you don't know what y is though, right? So we don't know. I don't really know how I would do it unless I knew what y is. Shouldn't it be e to the t minus 1? Well, notice here we have e to the at f of s minus a, right? So it's not e to the t minus a up here, right? Hopefully this might be a little bit small. Let me write it a little bit bigger so you can actually see properly. So Laplace inverse of f of s minus a, which that thing is sometimes written as Laplace inverse of f of s. Okay, s goes to s minus a. Okay, that's what the notation means. It just means this, but it's just a wonky way of doing it. Is e to the at f of t. So what you're saying there, you're confusing it with it's e to the at. It's not e to the t minus a. Right, it's e to the at, positive at. So yeah. Anyways, you can get a better picture of this in my notes. Yeah, no problem. Happy to answer questions. But yeah, that's the issue. Okay, so yeah, any questions? Yeah.
Yeah. Do we have to show that step for the first translation theorem on the test, or can we just use the table method?
I don't know what they exactly allow if they allow you to have a table. Maybe someone knows the answer to that. Is a table? I have a feeling I can't imagine a table is allowed. Yeah, for Laplace stuff. So yeah, you would have to show the first translation theorem, I guess, at that point. Or maybe you can just say you memorized it. I don't know. Like that's another option too, right? But yeah, just memorize the whole table. Oh yeah, before I forget, I want to just shed a little bit of light on this textbook that I really like. All of my friends have heard about it. So there's this textbook for this course, as well as vector calculus. That's very, very good. It is it's called Advanced Engineering Mathematics by Dennis G. Zill. You can message me after if you want to get a copy of it. I can help you find a copy of it. And very, very good. I love it. It's really good to read, and it has lots of good examples. and it's just like a really good one. So it has all the stuff we did before. It has Laplace transforms, and then it has Fourier series here, and then it has the whole section on vector calculus. Everything we're going to do in vector calculus is here, and so I highly recommend it if you want. So yeah, well, I just clicked by accident, but here's a vector calculus section, right? It has just like a lot of good explanations and examples and graphics, and it's just a very good textbook. So again, this is the title and everything like that. So if you'd like to get a copy, just see that. But is this textbook better than the textbook in the course outline? I would say for sure. Especially the differential equation textbook. I really didn't like the differential equation textbook, but I know we're past that now, so it's not that helpful anymore. But yes, I would say for sure. And I don't think the OpenStack textbooks are very bad, so I think they're pretty good. But I'd say this is just better. I think this is just a really good, like exceptionally good textbook. This is the one they used before. Yeah, it's the one they used before. Yeah, Jasper, you're right. I'm sure you know you're right. But this is the one they used to use. I don't know why they changed it. It's a very good textbook. I even have it labeled in my computer as MTH 312 because I got it last semester or whatever, because I knew I'd be taking this course. And that's what they usually use, but anyways. Okay, that's just a side note. If you want to get the copy of it, just message me after and we can figure something out. Okay, so let's take a look at the next example I have. Okay, so those are my Laplace examples. Any other questions about Laplace? Pretty much, that's what any other stuff about that. Otherwise, we can move on to Fourier series. And there's quite a bit in Fourier series. But any questions before I move on? I'll have a drink of my water while I'm waiting. Okay. So, yes, that was quick. Thank you. To do this thing or drink my water. So we have Fourier series to go on to now. Okay, so I don't think I have to go too much in depth about, like, I'd love to go and explain Fourier series. This textbook has a great explanation. So if our professor's explanation didn't quite do it for you, there's a great explanation of how Fourier series, how you derive all of them in this textbook, which I recommend taking a look at. It's all based on vector stuff, so if you're a little bit rusty on your linear algebra, it might be a little bit confusing, but I do recommend. The general thing is just the formulas, right? The Fourier series, like the formulas. That's all it is. So if I just take a look at them quickly here, I will just show you. We won't really talk about inner products and stuff like that. That's only really mentioned to be able to derive the Fourier series, right? So that's why I mentioned it. But if anyone has an example they want to go through, I don't mind. And so essentially, there is just a few topics I want to just talk about. So a function has a Fourier series, right? You can write a function as a Fourier series. This is how you do it. Just follow the formula. There it is. Inner product of functions, not inner product of Fourier. Inner product of functions to derive the Fourier series is what I meant, if I said that wrong. But yes, that would be difficult to do inner product of Fourier series. Okay, so then this is an important theorem. What does it converge to? We'll do an example where this actually comes up. But what does the Fourier series converge to? So importantly, f of x has to only be piecewise smooth. Okay, so a Taylor series was, had to be a continuous function. Obviously, there's a little bit of, there's asterisks on that. There's a bunch of conditions, but a Taylor series had a little bit more conditions. But Fourier series is a very loose condition that has to be piecewise smooth, meaning it's piecewise continuous, as in it's made up of a bunch of piecewise functions that have no infinite jump discontinuity, so no asymptotes or anything like that. It's like a little bit of a looser definition. And then smooth just means its derivative is also piecewise continuous. And so, yeah, we can just use that. And so lots and lots of functions are that, many more than the continuous functions. And we usually define it on some sort of symmetric interval. Anyways, you know all this. So what does it converge to is the point that I want to get at here. So if you are in the bounds, right, if this is your function, let's just say, let me just do a little graph here quickly. This is your x-axis or t-axis or whatever. This is your y-axis. And let's say this is the function. I'll do it in blue. This is the function. So it's a little unit step function or whatever, right? Or how about I do? Where's my tablet being weird? I think the button's stuck. Okay. So let's just say that is our function. For whatever reason, we want to do that, right? and it's, let's say it's symmetric over some interval, whatever. It's the same over here. The period is one symmetry. So the Fourier series is going to look like this. So I'll do the Fourier series in red. So the Fourier series is going to look like this. It's going to look kind of like that, and then like this, and then like this, and then like this. And there's a couple important features of this. I guess I should actually mention what's on the other side. So let's just say it does a little something like this, a little something like that, and it just continues sort of like this. Okay, it's kind of important to mention this, right? So okay, let's say that is our Fourier series. So the Fourier series would look something like this. Okay, so it's not actually going to be a vertical drop there, but let's just say I'm taking the limit as this goes to infinity pretty well, right? So the most important thing that I'm getting at here is that at the discontinuities, the Fourier series takes the average. Okay, it takes the average of the two endpoints. Okay, so average of the two endpoints. Oh, and then I should mention here, right? The Fourier series will also go. It will go up to discontinuous x equals L. Limit is so it'll go up to this this midpoint here, right? It'll go up to this midpoint right there. It'll go down like that too. Okay, so the red dots are what I'm trying to get at here. That's why I'm mentioning all this, right? Because at the discontinuities and at the edges, it will just take the sort of like average kind of thing going on here, right? The endpoints are going to be at the same place. That's what this bottom is saying, is that if we are at the endpoints, right, just take the average of the two endpoints. Negative L from the right, negative L from the left, right? And then divide by 2. And then otherwise, just take the average of the limits as you approach either side here, right? So it's going to look like this, right? That's kind of what your Fourier series is going to look like. So just important to mention that. I have an example where that comes up. So, okay. And then these questions are just questions that I've collected from people sending me, and just that I've seen that are interesting. And so from no particular place, I don't know where I got most of them. So yeah, we can just go right here. They're not particularly unique questions, but they just are interesting enough to mention. Let me just start with my first example here. So let's do the Fourier series of absolute value of sine x. Okay, so first example is the Fourier series of the absolute value of sine x. Okay, and so let me see, Fourier series, find the Fourier series. Yeah. So let's, of course, take a little, make a little graph of this. It's good to just visualize it before we start. Obviously, you don't need to visualize it. You can just jump right into the calculations, but let's do it anyways. So the absolute value of sine x looks a little something like this, right? So it's just something like that. Let me just take a quick screenshot here. Put it there. Okay, so there's our absolute value of sine x. And what you want to notice is that it's even, right? It's an even function. And so that's going to come in useful because the Fourier series is going to simplify at that point, right? Sorry, someone said, what are the bounds? Oh yeah, what are the bounds of the Fourier series? Yeah, good point. I do have to mention that. Negative pi to pi. Good point. I just forgot that because I was just focusing on the function for a second. But yeah, good point. So we have, this is our graph. It's even, right? That's the thing I want to note here. It's symmetrical over the y-axis. So because of this, I'll go ahead and do it, right? But you can actually just jump right to what's the cosine series, right? Let me just find that here quickly. So these are the cosine and sine. The formulas simplify if we have an even or odd function. So an even function will simplify to this, right? And an odd function will simplify to this. So an even function is a little bit simpler, right? So I'm going to note that it's even. So that means we can just jump right to this section here. And so we can just start calculating. A naught, right, is our first thing. I like to do it in this form, right? So A naught over 2 is what's going to be put there to add, but we can just calculate A naught there first, right? So that's going to be, okay, well, it's going to be 2 over P, which is pi, integral 0 to pi of the absolute value of sine x dx, right? So that's what A naught's going to be. Okay, now how do we calculate this? How do you deal with absolute value? Well, you just essentially say, we're lucky here, is that if you look at the absolute value of sine x, which is from 0 to pi, which is right there, and if you imagine what sine x would be the exact same function in that interval, right? sine x would be exactly the same, which is just the lucky part of that we're integrating from 0 to pi. So we just can just drop the absolute values. No issues. Right. Maybe just for complete clarity, I'll rewrite it, just so in case someone's reading this after. This is equal to the absolute without the absolute value. Okay, and then from here, this is the.
I'm sorry. Could you just explain how the absolute value drops?
Yeah. Well, compare. Essentially, we want to just compare sine x and the absolute value of sine x. Okay, but not just anywhere on the interval, right? Negative pi, 0 to pi. That's what I'm trying to say, right? 0 to pi. So I will draw this one in red, and I'll draw this one in blue, right? So in blue, well, let's start with sine x, I guess, right? So this is going to be half the period, right? The period is 2 pi. So sine is going to look a little something like this. Do you agree? That makes sense? Sine's going to look like that.
Oh yeah, I see.
Right?
I see now.
And now the absolute value of sine x is just going to be this, right? But then it's going to start going up like that. But that doesn't matter. We're just looking from 0 to pi. Right? We're just looking at 0 to pi. So from 0 to pi, they are the same function. There's no difference. They are equal. Okay, someone was asking, how do I set up a naught, an, and bn if f of x was piecewise? I have an example for that. Okay, so we will do that. We will do that next. Okay, we'll do it piecewise. Okay, so then anyways, for here, we can continue. We can just do integral of sine is negative cosine of x, right? Evaluated 0 to pi. We just have 2 over pi, and this is going to be negative cosine of pi minus negative 1, right? Because cosine of 0 is 1. Just put that there. So this is going to be 2 over pi. Cosine of pi, I got to think about that for a second. Pi would be here, so it's the negative 1. So it's going to be negative 1 plus 1, so it's going to be 2. So we're just going to get 4 over pi here. 4 over pi. Right, so there's our a naught. So that means that our function, I'm not quite ready to write the whole thing, but it's going to, remember, it's a naught over 2. A naught over 2. Right, that's going to go there. So a naught over 2 is going to be 4 over pi over 2, which is going to be 2 over pi. So it's going to be 2 over pi plus the sum n goes from 1 to infinity of now an cosine n, well, nx, right? Because it's n pi x over p, but p equals pi. P equals pi. That's our range here. So the pi's cancel. And we just get that. Okay, so now we got to find an. I just wrote that just so that you can see that even though I got 4 over pi, the actual number that's going to go here is 2 over pi. That might be a confusing way of doing it. I don't blame you. So for some people, you might want to just immediately divide by 2 here, right? Write that maybe as 2 on the bottom there or something like that. But I think it just makes the formulas more relatively the same if you just divide by 2 after. Just remember to do that. Remember that's a naught over 2. That's our first term. Okay, anyway, so an now, this is just going to take it doesn't take too long. So an, if we just take a look, for cosine series is 2 over pi, so 2 over pi, integral 0 to pi, of f of x cosine n pi x over p. So absolute value of sine x cosine n pi x over pi, right? But the pi's cancel, right? Tx. And remember that the absolute value of sine x over this interval is equal to sine x. So this is going to be 2 over pi, right? Right. I'll let you respond to that. Sine x cosine nx dx. Okay, so now we just have this integral to do, and that's going to be our an. And we just got to remember the formula here, which is that sine alpha cosine beta equals 1/2. Okay, sine. I don't know my board in front of me. Alpha minus beta. Okay, plus sine alpha plus beta. Okay, that's just a formula to remember. Your trig identities. So recall this. And so now that I recall this from my memory, This is 2 over pi integral 0 to pi of, okay, so it's going to be 1/2, right? And then times sine x minus nx plus sine x plus nx, close the bracket dx, right? Okay, now this integral can simplify a little bit here. So it's going to be, well, it's going to be 1 over pi, right? Because the 2 and the 2 cancel there. Let's write that out here. 2 and the 2 cancel. And there's going to be integral 0 to pi of sine. Now I'm going to write this a little bit differently. X 1 minus n, like that, right? Just factor out the x from the inside the bracket. And then just separate the integrals as well, right? So 1 over pi. Don't forget to move that 1 over pi to this integral as well. Integral 0 to pi of sine x 1 plus n dx. So used a couple rules in there, but hopefully that makes sense why we did that. And now these are straightforward to integrate. So it's going to be 1 over pi. Okay, and now the integral of sine is negative cos, but we have to account for that little constant. So negative 1 over negative n, 1 over 1 minus n, I mean, cosine x 1 minus n. Okay, evaluated 0 to pi, plus 1 over pi. Okay, and now this one's going to be the same thing. Negative 1 over 1 plus n this time, cosine of x 1 plus n, evaluated 0 to pi. So hopefully that makes sense how I integrated that. If not, let me know. Yes, second. And so now we can just start working on this. So it's going to be 1 over pi. Okay, now negative 1 over 1 minus n, cosine of pi 1 minus n, right? Plus 1 over 1 minus n, cosine of 0, right? Just 1. We can just deal with that after. Plus 1 over pi, and now a very similar thing. It's going to be negative 1 over 1 plus n, cosine of pi 1 plus n, okay? Plus 1 over 1 plus n, cosine of 0. And so these will just leave because they're 1. Right? Those are just 1. And now these guys, this is where it gets a little bit tricky. Cosine of 1 minus n, I, until very recently, thought this was negative 1 to the n, but it actually isn't. So cosine, I'm going to write this here quickly. Cosine of n pi equals negative 1 to the n. And the reason for that, right, is, if I just really quickly make a little visual here, right, the reason for that is that we have, our function f of x equals cos x, right? And then if you just imagine what's happening at those particular intervals, so let me just do this quickly. Oh, sorry, I meant a equals. Okay, and then f of, no, I'll plot these points. X equals IA. There we go. We have that. And a f of IA. Whoops, that didn't work. Why didn't that work? No, f of. Did that just be pi? That should be a there. Yeah. Okay. I don't know why that changed anything, but it did. Whatever. So I like visualizing things like this, right? Oh, that's not right. Why is that not right? I don't know why the vertical lines are not in the right place. Why are they not in the right place? They are at x equals a. Yeah, okay, that worked that time for some reason. Way too big. Anyways, the point is that if you just visualize this, right, you can see that at these vertical line, these dotted lines, right, that's what we're doing. We're going 0, 1, 2, 3, 4, 5, or whatever like that. So if n is 0, or if n is any even number, right, it's just going to be 1, and if otherwise it's going to be negative 1. But the issue is at minus 1. So there's nothing wrong with this formula. This formula here is correct, but it is not the same thing as cos of pi, n plus or minus 1, right? Or we can essentially use, well, I'll say 1 plus or minus n. That'll be a little bit more applicable. So that's actually a negative 1 to the n plus 1, because you see when n, so in this original case, when n was even, right, then we have a positive number, which is fine, right? That's what this says. If n is even, we have a positive 1. But when we're talking about n plus 1, if n is even, when I put it in, it's either going to go to 3 or it's going to go to 2 to 1, right? Because we're doing 1 plus or minus 1 or whatever. You're just going off by 1 there, right? And so it's going to be a different thing there. So like, for example, if I was doing cosine of pi, right, 1 plus 2, right, that's cosine of 3 pi, right? Cosine of 3 pi is going to be, so 0 pi, 1 pi, 2 pi, 3 pi, -1. So even though my input was even, my output was -1. So it's going to be off by, it's going to be the opposite. So it actually doesn't matter if you put a +1 or -1 here, but +1 is there. So hopefully that made sense as to why that's the formula for plus or minus 1 there. It's n plus 1. So I'm going to use that, 1 over pi. It's going to be -1, -1 to the n plus 1 over 1 minus n, plus 1 over 1 minus n, plus 1 over pi, and it's going to be -1. Yeah, it makes sense. Never really thought about it. Yeah, fair enough. I wouldn't really think about it either, but since I'm doing this, I thought about it. 1 plus n plus 1 over 1 plus n. There we go. And so we have that there like this. This is being recorded, yes. I should check, but yes, I checked before. We're good. Okay, so we have this, and then I'm just going to now start combining things because this looks really bad, so like really messy. This is obviously not the final form. So this is just going to be, these are like terms. It's going to be 1 minus -1 to the n plus 1 over 1 minus n plus 1 minus -1 to the n plus 1 over 1 plus n. We have that, so that went from that to that. So I'll leave that on the screen in case people want to see. And now we want to get common denominators, right? So I'm going to multiply by 1 plus n on the top and bottom here. So 1 plus n. And then here I'm going to multiply by 1 minus n. 1 minus n. I guess that should be in brackets too. I'm going to multiply that there. So I'll just write it all out. So 1 minus -1 to the n plus 1 in brackets 1 plus n plus 1 minus n times 1 minus -1 to the n plus 1 all over, and that denominator is just a difference of squares. 1 squared minus n squared. That's the point. Okay, now we just got a little bit of simplification to do, but you're going to see that some things cancel. So 1 times 1 is 1. 1 times n is n. That times 1 is that. Negative plus 1. That times that is -n, -1 to the n plus 1, plus 1, minus -1 to the n plus 1, minus n, plus n, -1 to the n plus 1. Okay, so just foiled everything. 1 minus n squared. Just foiled everything. I did that fast, but if anyone is confused by a step, just tell me and I can explain it. But that cancels with that. That cancels with that, right? So all we're left with is, there be a 2 in the front? Did I lose a 2 somehow? No, I don't think I lost a 2. I'll check my solution. 1 over pi, okay, and this is going to be 2 minus 2, -1 to the n plus 1 over 1 minus n squared. Simplifies a lot there. Right, and so it's going to be 2 over pi, 1 minus -1 to the n plus 1 over 1 minus n squared. Let me check my answer for this originally, but that sounds right to me. Let's take a look. 1 minus n plus 1 over 1 minus n squared. Yep, perfect. Okay, good. So that's our an. And so just finally, before anyone has any questions, let's just say f of x equals, so it was 2 over pi plus the sum, n goes from 1 to infinity of that. So I'll put the 2 over pi in the front, and it's going to be 1 minus -1 to the n plus 1 over 1 minus n squared cosine of nx. There we go. That is our Fourier series. Any questions? Can we change n plus 1, negative n plus 1? Yes, you probably, yes, that makes sense. You can do that. Yeah. Oh no, not n plus, no, plus 2. N plus 2. You'd have to change it to n plus 2. Because it's
doesn't -1 does that simplifies to -1 to the n?
It's going to be -1 times -1, so -1 to the 1 n plus 1, which is going to be -1 to the n plus 1 plus 1. It's going to be -1 to the n plus 2. So you can write that.
Well, that's the same as -1 to the n, no?
To the n plus 2. Oh, that is the same as negative. Yeah. Yes, that is the same as -1 to the n. Yes, you're right. That just so
Wait,
happens.
wouldn't the series start from 2 and then you have to check for A1?
Oh, series start at 2 and you have to check for A1. Yeah, because you're right, because 1 is undefined, right? So 1 is a root of the denominator, and so you have that there. Yeah, A1 would just be, yeah.
That's strange. I thought if something like that happens, the solution wouldn't work. Like we would have encountered some issue while we're trying to solve for a, but we didn't.
We didn't. This actually does work. I checked with the graph, so it does actually, everything's fine with it. Yeah, is there anything we're supposed to do at this point? I don't know if there's anything we're supposed to do to correct this. There's nothing really wrong. It does. I mean, you're right that this should start at 2. This has to start at 2, because that's a zeros are 1, and yeah, whatever. The important 0 is 1, and so we have here just that you can't have n equal to 1. To start from 2, and then I don't think there's anything else you have to account for, because if you just graph it, let's graph it quickly. I'll show you actually. Take a minute and just show you how I graph Fourier series in case anybody wants to just graph it to make sure you're right. So I'll you put on the restriction that n cannot equal 1. Yeah, it makes sense. So just to quickly show you how I graph it, so I'm just gonna say f of x equals the absolute value of sine x, not 6, sine x. There we go. And then now to graph my Fourier series, I like to just make a separate function quickly here of the coefficients, right? So the coefficients are, it was 1 minus -1 to the n plus 1, and 1 minus n squared. Oh, sorry, that's the denominator. 1 minus n squared, right? That graph doesn't matter. Like, they don't care about the graph. And then we just actually start drawing out our function. G of x equals 2 over pi plus 2 over pi times, and then I just say a of 2 cosine of 2x, already good. A of 3 cosine of 3x, and I'll just go that far. You can add as many terms as you want there. So a little bit of a we get a Desmos masterclass from Adam. Yeah. I will also show you guys how to graph parametric stuff in GeoGebra. It's not that hard. So I will show, when we get to the parametric stuff, I will show that.
If you just type in sum, you can get the summation symbol.
If I type in, oh yeah, but does it actually function?
It doesn't function for infinity. I tried it. It function it gives you a close enough graph for n equals 1 and goes till 10.
Oh, really? Does it?
Yeah.
So 2 over pi plus, if I say 2 over pi, and I just say sum. Oh yeah, n equals 1 to just say.
Don't try anything above 10 because it breaks your computer.
Okay, I'll say 9 to be safe. A of n cosine of n pi. Enter. I don't see it. Is it my computer that's not functioning?
Oh, because you're starting from 1. It won't work if it.
Oh yeah. Start from 2 there. Okay. Oh, it didn't like it. Didn't like it for some reason. Yeah, I don't know. But does that, yeah, it's just not liking the way I'm typing it. 2 over pi 9. Is it the bounds too big? No. An cos n pi. I don't know honestly why it's doing this, but
you don't have the n pi x. You just have n pi.
Oh yeah, n pi x. You're right. Oh, it still doesn't like it.
Oh wait.
Oh, it's just supposed to be nx. That's why. It's just supposed to be nx. That's it. Right? There we go. And so there we go. Good. Okay. Nice. I don't have to type it manually now. Thank you for sharing. Okay. So let's continue now then with the next example. So hopefully that makes sense. Any questions about this? Any questions about this one?
Are you gonna do a piecewise version now?
Yes, I'm going to do a piecewise version. Yeah. How do I deal with the n equals 1 case? I just don't. Oh yeah, bn. That's true. How did I know bn wasn't included? Well, I just noted that it was even. So anytime you have an even function, if I tried to calculate bn, it would be 0. So let me show you why. Bn is going to be, if I just try to do it by the normal Fourier series. Oh, I lost it. Where's the normal Fourier series? It's going to be 1 over pi integral negative pi to pi. So it's going to be 1 over pi integral negative pi to pi of, and now we just say f of x sine whatever. So absolute value of sine x sine nx, right? Because n pi x over p, and then p is pi, so just cancel that, dx. And so this is an even function times an odd function, not even. No, sorry, even times an odd. Even times odd is odd, right? The integral of an odd function over a symmetrical range is equal to 0. Always. Can you skip bn if the bounds are 0 to pi? So we will deal with 0 to pi. Yes, we will deal with that. Can you skip bn if the bounds are 0 to pi? No, it does matter what you choose if you're doing 0 to pi. So you can, I guess you can, but it depends on what the question asks you. So we'll do that. In fact, that might be the next question. Let's see what's next here. Find the half-range Fourier series. Yeah, okay. So let's try this one. I have another example here, just randomly. So we have our function f. So this is the next example. Right, this is f of x equals piecewise function 1, 0. It's not a complicated piecewise function, but it's defined 0 to x, 0 to 1/2. I mean, sorry, 0 to 1/2, and then 1/2, right, to 1, including 1/2. I guess I don't know why it's including that. Okay, so there's this one, and so of course it's just find the Fourier series. That's the prompt. So let's try it out. Let's take a look at what's going on here. So first of all, our Fourier series is from 0 to 1, right? It's defined 0 to 1, right? So we have to do what's called a half-range extension in this case, right? And so, oh, and I should be clear, like the prompt is that we do, let me find it. The prompt is that we do the Fourier sine series. But you actually have a couple choices. You can actually do a Fourier series, you can do a cosine series, or you can do a sine series. And you'll get 3 different series depending on what the question prompts you to do. Now this is a little, it's a little complicated. I don't know how much we're going to actually be asked to do this because he didn't talk very much about this, and there's a lot more that he could have talked about. But again, if I go to this, my favorite textbook, and I take a look here, we just see this is, here's the half-range extensions. Okay, so if we're doing the Fourier series for, this example here is slightly different, but it is the Fourier series for x squared on 0 to L. They just did it in general from 0 to L. Well, this is what it looks like. This is what it looks like if you do the cosine series. The cosine series is assuming that it's even. It's saying, let's extend, right? Let's extend the Fourier series from, we can't actually do it from 0 to L. We can do it from negative L to L though, right? We can do this much. But we have to somehow assign what the function is on this other end. So if you do the cosine series, you're assuming it's even, right? And to be clear, this is even, sure, but it's even on 0 to L. When you do the cosine series, you're extending it and you're saying that it's even on negative L to L, okay? Here, with the sine series, so you see how we end up getting with this little parabola that repeats like that, right? If you do the sine series, you're saying it's odd on negative L to L. And if that were true, then the shape of the graph would be something like this, right? An odd thing like that. And then if you do the Fourier series, right? And again, this is all starting with something on 0 to L, right? If it's starting on negative L to L, you only have one option. It's just the Fourier series. You just do it. But if it's on 0 to L, you are arbitrarily assigning what the other side of the function is, right? Is it even, is it odd, or is it neither? In this case, it's a little bit tricky. So I should be clear here. Here you just say P equals L. P equals L. Here you make a little bit of a different choice. Here we're saying it's neither on 0 to L. So the entire period happens in a span of L, right? But we want that to be centered. So we center it instead in that. But notice that that is the same period. If that were to be repeated, if the red section were repeated infinitely, or if the green section were repeated infinitely, either way, that would get you the same function at the end. Right? Oh, sorry, there might have been some question. Let me just see what people. So test the bounds we always use. So on the test, the bounds will always be negative L to L. Not sure. Not yet. Not. You do sometimes have 0 to L. He did also talk about it in the lecture. Actually, he said don't worry about this. Then again, he said that about reduction of order, and that came up. Yeah. So I don't know. I have a feeling this last case won't be there because that's a little bit complicated to deal with. But these first two cases, it's not too crazy. You just choose one of them, and you just do that exactly by the formula. So in this case, we say that the p-value is L over 2, right? L over 2, because you're going from L over 2 to negative L over 2. Although there's some weird calculations they do in this. So if you want an example of this, we might be able to do it, but I'll have to do the example in the textbook that I gave because it's a little bit weird. But anyways, we can answer this question for now. And it tells us to do the sine series. So what that means, since it's telling us to do the sine series, I'll just copy this down a little bit here, right? So again, this discussion right here was not for this particular function, it was for x squared, just because that's the one they have in the book here. With this example, it told us to do a sine series. And so if I take a quick sketch of it, what that actually means here is this. I will sketch this out a little bit. And this, like that. Okay. So from 0 to a half, this is going to be our 1 point. This is going to be our 1/2 point. This is going to be our negative 1/2, and this is going to be our negative 1. So from 0 to a half, it is 1. And then I get both ends, not including for some reason. I think that's a typo. That should be including that end, I think. And then from a half to 1, it is 0. Not including that. So there we go. We have that. By doing the sine series, we're saying it's odd. We're saying, okay, I can't actually do a Fourier series from 0 to 1. What I can do is I can do a Fourier series from -1 to 1, and I have to assign what the function is from -1 to 0. So by doing the sine series, you are assuming that it is odd, and so that you would get this. This is what the function would look like that. Because it has to be odd, right? It has to be reflected across this line, like that. That's the definition of odd. And so this would repeat, right? This would repeat then, on and on and on, from -1 to 1 there. Okay, but anyway, so we're doing so we're doing the sine series. Any questions about this though? What I just described right there, right? If it was a cosine series, it would be this. Am I allowed to do this? No, I'm not allowed to do this. If it was a cosine series, if we did the cosine one, it would be this. Yeah, it would be this. That. No, that doesn't make sense. I mean, I can't decide if the endpoints are included or not, but the shape is right. I just can't decide if the endpoints are included. Does that make sense? If we did the cosine, that's if we did the cosine series. Okay. And if we did the Fourier series, it would just be this. It would be this like that. And ignore it. That's not there. I just can't erase it because I'm gonna leave it there. There you go. That's what it would look like if it was the Fourier series. So, but since it's the sine series again, we're assuming it's odd, so it's gonna look like this. Whoops. Like this. So we got this like that. There we go. Oops. Okay, so since now this is what it looks like, right? You don't have to draw this to be able to answer the question, but just to get an idea of what the graph is going to look like, that is what the graph is going to look like. So now let's go ahead and actually do this sine Fourier series, right? Sorry, one note's being weird. as always. Notice OneNote's a weird one. Let's see, can I open up a new OneNote? Just open this up. There. Okay. There. Better? I think that's good. Now it's not going to be weird. Okay. Sometimes OneNote just needs to be restarted. Okay, so now that we have this, I can go ahead and just do the sine series. So, you know, I haven't done a full Fourier series, but that's okay. So it's going to be last one was a cosine series. This one's going to be a sine series, right? So that's just going to be B. All we need is Bn, right? If I just get the formula up here, all we need for this particular case is just B. Right? Where did I lost it now? There we go. There we have our Bn. And okay, so let's go ahead and do it. So for it doesn't matter, like we're claiming it's odd, right? It doesn't matter if this function is actually odd, right? We're claiming it's odd from negative L to negative 1 to 1, right? From negative 1 to 1. You're claiming it's odd. So we can just go ahead and do the odd, the sine one, right? So it's going to be Bn. Bn is going to be 2 over 1, right? 2 over 1. Integral, odd. Yeah, 2 over 1 integral of, that formula's right. That's not wrong, right? Yeah, okay, I got that right, yeah. 2 over 1 integral 0 to 1 sine of n pi x dx, right? Oh, and the function. The function has to be in there too. So integral of 0 to 1 of f of x, right, sine n pi x. Let me get my solution up for this one. I feel like I can feel myself about to make a mistake, so let me get my solution. I don't plan for this one. I do. Oh, I think I wrote it on a different spot. No, I didn't. Yeah, we're good. Okay. So now that that's the function there, now I just got to separate it because the function changes its definition in 0 to 1. It changes from at a half, right? So I got to write this as 2 integral 0 to 1/2 of, now what is f of x in that interval? It's 1, right? So 1 sine n pi x dx. And then I want to add the other one, which is 1/2 to 1. And what is it in that interval? Well, it's 0 times sine n pi x dx. Well, integral of 0 is 0, so that just goes away, lucky us. And so all we have is this right here, which is really simple to calculate. So 0 to 1/2 of sine n pi x dx. Okay, well, that's just going to be 2 times negative 1 over n pi cosine n pi x evaluated from 0 to 1/2. And then we have this here. Now we just evaluate this. So it's going to be negative 1 over negative pi, n pi, cosine of n pi over 2. Okay. And then I want to add 1 over n pi cosine of 0. Cosine of 0 is 1, but just say cosine of 0 there. All right, okay, well, negative, so it's going to be negative 2 over n pi cosine of n pi over 2, okay, plus 2 over n pi, because cosine of 0 is 1. And then I think that's as far as I went. I don't think I simplified it anymore because I don't think I could figure out what cosine of n pi is. Maybe you want to try to figure it out together. Let's see if there's any formula. I don't know if there's any formula that simplifies that.
I think for this one, it doesn't have.
Oh, I remember looking at this. Yeah, you don't think so? Yeah, I agree. It looks like it's a piecewise one. So if n is a multiple of 2, then it's negative 1 or 1. Oh, sorry. If it's a multiple of 4, it's okay. If it's a multiple of 4, it is positive 1. If it's a multiple of 2, it's negative 1. And if it's a multiple of, if it's 1 more than a multiple of 2, it's 0. So it's just too complicated at this point to write it all down. So you just leave it like that. That would be like some wicked piecewise function. So no need to overcomplicate it, but that's our Bn then. I don't even have to rewrite it. Bn is that. And so our function f of x, well, it's just, so I can just factor out 2 over n pi. So it's going to, not n, sorry, it's 2 over pi times the sum. N goes from 1 to infinity of 1 over n minus 1 over n cosine n pi over 2. And then we want to multiply that by sine n pi x. And there's our series there. Okay, so let's graph it quickly and make sure that it's all up to par, making sure that it is what we expect it to be. So first of all, how do you graph a piecewise function in Desmos? Where'd the sine come from? The sine just came from the formula for here, right? So what we just did is we calculated bn, but then in the actual Fourier series, you need to do bn sine n pi x over p. P is 1 in our case, so it's just n pi x. Right? That's all it is. I just calculated bn and then multiplied it by sine. Okay, good. So let's just quickly graph it just to make sure it works out. So the prompt, the actual function was, so it's 1. Whoops, I don't know what I clicked. Click something, but now Zoom went horizontal for some reason. Anyways, let me show you how I write that. So to graph it, I say, okay, y equals 1. That's the first function, but from where to where? Is there a theorem sheet for this midterm? I don't know. I have my notes. You can look at my notes, I guess, but I don't know. That's the sheet, I would say. So from where to where? Well, it's from 0 between x is like this. So you write it like that. That's how you write it. You just immediately put the set brackets after the function, and you do that. And then y equals 0 goes from 1 half, do that, x 1 like that. So there is our other. That's our function altogether there. I'll make them both red. Now that I have them both red, I can, actually graph them. Actually graph our function. So our function, again, I like to do, what I like to do is I like to write the coefficients out separately. So the coefficients that I got were, so it was an equals, and it was 1 over n, oops, 1 over n, okay, minus 1 over n cos n pi over 2. Okay, great. So we don't actually care about that graph. We just care about its numbers. And then now I'm going to do the thing. So it's going to be 2 over pi, right? That was what we had here. So I'm going to write this 2 over pi. And then we want to multiply that by this whole thing. Did I write the 1 over n minus 1 over n and pi? Yeah. And so then I'm just going to do the amazing new thing that I just learned. I'll just say 7, and it's going to be an sine n pi x, and we get something like this. And then as I increase this here, will it increase? No, I think I have to do that. Here, can I set this to some slider? Let's see. Oh, it has to be step 0 to. Let's say I'm going to be risky and say 0 to 20. Step of 1. Let's see. So as I increase, let's see, it does approximate it better. Looks like I can get up to 20. No problems here. Where's that monster? Yeah, well, it's this function. It's the function that we got. That's the monster. And obviously we see the little Gibbs phenomenon going on here. It's just that at the discontinuities you have a little extra little error, but nonetheless it also goes away as the limit goes to infinity. Let me be a little risky. Let's see how high I can go. I don't want to crash anything, but let's say I go 50. Yeah, am I lagging? No, not lagging. Go to 30. See what's going on. 40. No problems. Okay, there we go. There's our Fourier series. Anyways, but notice that it is what I said, right? Notice that it is going to go 1, so 1, 0, and then on the other side, it's going to pretend like it's odd, right? So it's going to go 1, 0, and then it's going to do a periodic extension of that. So from the lines x equals -1, which is right there, to x equals 1, that little frame right there that you see, I'll make them both blue, that little set is going to keep repeating, right? So that's why you get this little flat section there, because that goes there. Okay, but anyways, there's this. There you go. That's that. That's the function. So let me have a glass of water. And any questions about this question?
Can you go back to the actual work solution? I have a
The
question.
solution, yeah, for sure. Okay, here.
Okay, scroll up a bit more. I was actually doing this, but just going straight at it. You see how you have the two parts of the piecewise function? Usually if you try to actually solve for a0 or n, you'll get 0, like without even checking, because you said you assumed it to be odd. But if you tried to use it for a naught or a n, you just get 0 because that's what I got.
Yeah, if you tried using it for an, you'd get 0. Yeah, you were doing the cosine series?
No, I was just doing the entire thing like fs. So a
Okay,
naught.
were you
an.
doing it from -1 to 1?
Actually, just I did it from -1 to 1.
Yeah.
Yeah.
Okay, if you do it from -1 to 1, but then you have to extend. So what did you do with the function is not defined from -1 to 0? Right?
Yeah.
So you must have added some information there to make it defined from -1 to 0.
He's right. Okay.
Right. So there's a complication there with that.
So wait, so with this piecewise function, you chose it to be sine, or is it because it looks odd you chose sine
No,
series?
you could have chosen sine or cosine or a regular Fourier series. Any of those three would have given you a slightly different series. Okay? Because like I was explaining here, like I chose sine, so it gives me this. If I chose a cosine series, then the graph would look like this instead. It would be that because I have to doing the cosine series is extending it in an even way. That's what the cosine series is doing. And then doing the Fourier series, if I did the Fourier series, it would extend it like this. It would just go up and down, up and down, up and down.
So would the bounds change though? Like
Yes,
from
yes, yes. So the sine and the cosine series would both be p equals 1. But then, and this is the part that sometimes I make some mistakes in, but I mean, according to the textbooks, if I'm doing so that's for sine and cosine. But if you just do the regular Fourier series, you're going to do a half.
Oh.
You're gonna say from 1/2, and that also kind of makes sense because if I'm saying this is, if I'm saying that this is all there is, it doesn't like it's not even or odd, then from here to here is the entire function, right? That is the entire function being repeated from -1/2 to 1/2, right? And so you pick that like that. Do you see that there? Does that make sense?
Yeah, okay.
Right. So then you have that.
Adam,
Yeah.
what happened? What like? Do you think it would A be possible, and B, how do we deal with the Fourier series that was not on an interval from -p to p, and it was also not on an interval of 0 to p?
You will not.
Like if it
have,
was
you
like,
will not have to deal with an example like that.
Okay.
You will not have to deal with it. Yeah. Good question. But yeah, you will simply not have to deal with that. I don't know. I don't know how. But yeah, that's a whole different thing. I think. I don't even know if it's possible. I'm not sure.
And just to clarify, we could have a question that's from the range -p to p, and it doesn't specify whether it was even or odd or maybe neither.
Yeah, you'd have to figure that out.
Okay, and if it's neither, then we would have to find an, bn, and a0.
Yeah.
Or a naught, I mean. Okay.
Yeah.
Yeah.
Exactly. Okay. That's actually pretty much all the Fourier I have planned. After this, I wanted to move on to some of the polar stuff, right? I have 2 polar questions to deal with. What time is it? Let's see. Are we here? Okay, so I have 26 minutes. So, of course, if we run out of questions, I can do it. But I can move on to polar time, yes. So is everybody ready for that? Sounds good? Sounds like 100 minutes to do 7 questions. Yeah, it is crazy that we have that much time to do so much. Okay, so let's take a look at this question. They're both from the homework, but I think they're both pretty complicated questions, and I think they're both worth the time to go over and to make sure people understand, because this is the kind of question that you try, you get it wrong, and you're just like, I'll try it again later, and then you never get to it. So let's try to really figure out this question here. So find the area of the common interior of r equals 4 sine 2 theta and r equals 2. So to get obviously a visual of this, we want to be able to graph it, right? So let me just graph it quickly, and then we can take a look at what's going on here. So the common interior of r equals 4 sine 3 theta. I think it might have been 2 theta. Was it 2 theta? Oh, I have it here. Yeah, 4 sine 2 theta, and the other bound was r equals 2. R equals 2. There we go. So that is what we want. So we want the common interior. And so what that's going to look like, take 2 screenshots really quickly here. What that's going to look like is this. Okay, so what we're searching for is this area like this. this. So like there, all that. Okay, and then same thing here, right? These are the four. These are the four ones like this, right? Okay, so I'll just fill it in just so we understand that we're looking for all of them. Okay, but the first thing to notice is that if I just find the area of one of them, that's enough. And I just multiply that by 4, right? They're symmetrical. It's all symmetrical. Okay, so that's the total area. But if I just found the area of just one of the pieces, that would be fine. So we can try to change the question. We can focus in on this. Okay, we can focus in on this picture like this. So now I'm just looking for this area in here. I'm not going to fill it all in because I need to be able to see. Okay, and let me just specify what our functions here. That's r equals 2, and this is r equals 2 what is it? Sorry.
4 sine 2 theta.
4 sine 2 theta. Thank you. 4 sine 2 theta. Okay. So now we want to be able to find that area. Okay, so what we're going to do, the way we're going to solve this is we're going to break it into a couple chunks. Okay, the first chunk, okay, so actually the first step would be find these intersection points. That's always just a really good first step. So let's find the intersection points. Intersection points. Okay, we just do that by setting the two equations equal to each other. So 4 sine 2 theta equals 2 sine 2 theta equals 2 over 4, right? Sine 2 theta equals 1/2. 2 theta equals sine inverse of 1/2. Right? 2 theta, theta equals 1/2 sine inverse of 1/2. Okay, so now we got to figure out sine inverse of 1/2, but we're actually interested in the first two solutions, right? Like inverse functions have infinite solutions. So we're interested in the first two. So sine inverse of 1/2 is pi over 6. So it's going to be theta equals, so the first solution is going to be 1/2. So theta 1 is 1/2 of pi over 6. And theta 2 is going to be 1/2 of, and now to find the next solution, you just remember your cast rule, right? So the first solution was in our first quadrant. The next solution is in the second quadrant because that's the next place where sine is positive. So to move an angle to the second quadrant, you do pi minus theta. So it's going to be pi minus pi over 6. That's what I'm trying to find right now. What are the intervals? I'm trying to find the intersection points to be able to determine the intervals. That's what I'm doing. Right. The bounds. Okay, so now we have this, right? We have this theta 1 and theta 2. Now I can just actually calculate this. So theta 1 is equal to pi over 12, and theta 2 is equal to 1/2 of, well, that's going to be 5 pi over 6, so 5 pi over 12. 5 pi over 12. So now, what that taught me is that I have a ray coming out like this from here to here. Maybe I'll make it actually go off the grid. And so we have here that is pi over 12. Okay, and then we have another one. We have another one like, let's go up. Another ray like that, and I'll bring it up to the top here. Isn't it 11 pi over 2? Well, that would be, no, I think that should be good. I think, remember pi is 6 pi over 6. Same thing as 6 pi over 6. So then minus would be 5 pi over 2. 5 pi over 6. 5 pi over 12. I think that's right. Yeah, okay, sounds good. Okay, and so then we have those two rays. This angle here is 5 pi over 12. Okay, that's that angle there. And so now we know that those are the two intersection points of these polar graphs. Okay, great. So the reason this is useful is because now, I'm going to erase these here just because it's going to clutter it up a little bit, but just remember this is the line for pi over 12, and this is the line for 5 pi over 12. So now we've separated this now into 3 areas. This area, like that. Okay. This area. Okay, this area, and finally this area. And all together, I shouldn't use yellow actually because that makes it look like it's the final answer. Now we can find the area of all these three pieces. Okay, they're all relatively simple to solve. All like much simpler than the whole big piece, right? So we have that whole area there.
Wait, sorry. So the blue area is not in the interval. So would it not be included?
It is included in the piece we're looking at. You see this piece here, right? So the blue areas kind of start like that. My lines are not ideal, but those are the blue areas. And you see they are included in this yellow section. So they are part of the final answer area. See that?
But we created the two thetas to find the area in between.
That's true, but the question was asking for the area enclosed by this graph and this graph, right? The common area enclosed by those two graphs.
Yeah, no,
And
I get what you're saying, but okay, I'm thinking of the actual lines. So whatever is in between those lines is the area that you're taking, but those are just it shouldn't be thought of that
those
way.
are just for intersections, right? Those are not like these lines here are not part of the graph that was given to us. They are just they're just there as guides for where the intersections are, right?
Yeah, no, I get it. Yeah.
Okay, so that means our final answer is going to be 4 times S1 plus S2 plus S3, right? 4 times because we need 4 of them, and then each one is S1 plus S2 plus S3. And it looks, I can't remember if it actually works, but it looks like S1 equals S3. I'm pretty sure that's fine. Let's not assume it for a second and see if we get the same answer, but I'm pretty sure, I think I just didn't do it with assuming S1 equals S3. They must equal, but anyways, let's just go at it like this. So now we got to find all these areas. Okay, so now let's figure it out. Now I'm gonna start. Why are we adding S1, S3? Aren't we only trying to find the area of S2? No, we're trying to find the area of this whole section in here, right? So what I highlighted in yellow, that is this whole section like this. That is this whole section like that. That is the yellow from up here, right? So again, these are those ray lines that I drew, right? But you see that the stuff outside of those ray lines are still included, right? They're still included there. Okay. So now that we have this, let's find all of those pieces. S1, well, let's start with S2. S2 is a little bit of the easier one. So let me just break it up into different steps here. So S1 will be there. S2, let's do that next. So I like to do it not with the double integral. The double integral is very useless most of the time. So the formula is 1/2 integral from theta 1 to theta 2 of f of theta, or just r squared d theta. Like that is the area enclosed by a polar graph. But it seems like we have to write it with the double integral for this test. I don't know. That's what I've been told. That we have to write it as in terms of the double integral, which will reduce to this formula always. Okay. So again, this is just the better way to do it, but to my understanding, we have to write it as a double integral for the test. So how you do it is, okay, so let's talk about integration here quickly, about how this works. What's happening in this picture?
Sorry, I gotta ask. Just that equation that you have, that area equation, that is derived from the double integral, right?
It is, yeah. It is derived from the double integral. Yeah. So how the integration, yes, you're right. It only reduces that as lower bound of 0. That's true. Yes. So, okay, slight incorrect of what I was saying there. But in this particular case, that is exactly what we have. And you can always do it, I'm pretty sure, always do it in terms of a bunch of them that have the lower bound of 0 and then just subtract. So I don't think there's any time that's absolutely necessary to do it that way. But anyways. So how this integral works, okay, how we integrate this area is, first of all, we imagine a bunch of rays coming out like this, right? So this ray like this, and this ray like this, and this ray like this, and we're adding together the lengths of all these rays, right? The lengths of all these rays. And that is how we integrate. In fact, we're integrating all of these rays. We can use the double integral on the midterm tomorrow. Yeah, I think you're supposed to use the double integral. You can use the double integral. You're supposed to. So anyways, we're trying to add together all these rays like this. So first of all, that's why we end up with this integral of r d theta, right? The rays r is the length, right? R is the length of our ray for a specific theta, and we're integrating theta across from pi over 12 to 5 pi over 12, right? But if we have to start with the formula for the double integral, how do you create one of these rays is the next question. And what you do is you create these rays by integrating the lengths, all these infinitely many dots, right, all the way from 0 to your maximum length. So what we're going to do when we explain that is that's the integral from 0 to 2 of r dr, right? That gets you a ray. That gets you one single ray. And then we want to integrate the rays from pi over 12 to 5 pi over 12 d theta. That's my understanding of how it works. Okay, again, I never actually use the double integral when I'm solving these questions, but that's how it. Why is it 0 to 2? Because these dots, they start at 0, they start at a length of 0, and they go to a length of 2. So we want to integrate from 0 to 2. Right, and so this is the area, right? So again, you're essentially, this first integral is creating one ray. The second integral is integrating all the rays across this from pi over 12 to 5 pi over 12. Again, that's my understanding of it. But look, what's going to happen is, yeah, it is cool, right? What's going to happen is that, well, 5 pi over 12, this is, all that is it's going to be r squared. So the integral of r dr is r squared over 2, right? Evaluated from 0 to 2, d theta, right? Okay, great. So the 1/2 goes out. Pi over 12, 5 pi over 12, r squared. That's all it is. And 2 is our upper function, so 2 squared d theta. And it's the same as this formula, right? It's the same as this formula that we got here, right? It's just, so there's not really a need to go through all this. It's only if you were like finding this area of this bulb here, not including the circle, then I guess it would be useful, but still you could do everything with this formula. And I think it is just better to do everything with this formula, in my opinion, than dealing with a double integral before we even really learned about double integrals, right? So that's the thing there, right? We never really learned about double integrals. We will, you know, we did. So, but yeah. So, anyways, this is going to be this integral 5 pi over 12 d theta. So that's going to be 2, and this is going to be 5 pi over 12 minus pi over 12. And so that's going to be 2 times 4 pi over 12, which is 8 pi over 12, which is 4 pi over 6, which is 2 pi over 3. Triple integrals is where it's at, yes. And there's our answer. 2 pi over 3 is for S2, not the whole question, S2. That's that. So hopefully that made sense of how I figured it out, right? That, again, I'm going to repeat that double integral thing here. The first integral is creating one ray. It's integrating all these lengths, right? And then the second integral is varying those rays, integrating all those rays from pi over 12 to 5 pi over 12. And that's creating the whole area, right? That gets our whole area. We're adding together infinitely many like lengths, infinitesimal lengths, and then we're adding together infinitely many infinitesimal rays that go across like that in order to get our area. Okay, great. So that's S2. The reason I just did S2 first is because this is a lot easier to explain with S2 than it is with S1. So with S1, we want to do something similar, right? We want to create a ray. Well, so the ray is the integral from 0 to our outer function, our outer bound there. Our outer bound is 4 sine 2 theta, right? That's our outer bound, 4 sine 2 theta of r dr. And then that we want to integrate d theta, but from where to where? Well, from 5 pi over 12, 5 pi over 12, right? From this ray like that, we want to add together all these rays. So up like, all these rays like this. So like this ray, right? All these rays together, we want to add all their lengths. In fact, we want to integrate all those lengths, all of them up until the ray is vertical, right? Perfectly vertical. Up until 2. right? So a little bit hard for me to draw, but hopefully you can see it. Rays coming out like this, all the way from the origin to the graph, origin to the graph, origin to the graph, and they're going to keep going more vertical, vertical, vertical until they are vertical. So we're integrating from 5 pi over 12, which is that purple line, all the way to pi over 2. But again, this just turns into 1/2 integral 5 pi over 12 pi over 2 of r squared, but r squared is going to be 4 squared sine 2 theta, sine squared 2 theta d theta. Why would we go beyond the upper boundary of the curve? What do you mean the upper boundary of the curve?
At first, I thought you were solving from the line that's at 5 pi over 12 to the red, the red petal, like the line outside. But then you said you're going to pi over 2. So it's like, are we trying to solve for S1? Why are we going beyond the upper boundary of
because
S1?
S1 is this, so it's all these raised together. Right?
Yeah.
All these angles are bigger than 5 pi over 12. All those angles are bigger, right?
Oh yeah, that makes
Right?
sense.
And
we
then
can't actually see it. There's some point right there that's actually at pi over 2.
Exactly, all the way to vertical, right?
Hey, that makes sense.
Right. Good. Whoops, lost the line. Why is it 1/2? Where's 1/2? Oh, 1/2. Well, that's just because integral of r is r squared over 2. So notice I have r squared over 2. Does that make sense? The integral of r dr is r squared over 2. And then I just apply the first bound, the upper bound, right? Yeah. So now we have, this is going to be 16 over 2 integral 5 pi over 12 to pi over 2 of sine squared, 2 theta d theta. It's going to be 8 integral 5 pi over 12 pi over 2. And now this one, we use one of the formulas, which I forget. Sine squared theta is, I think we use the one that's like 1, I have it here somewhere. Sine squared, no, actually it's not even written out, but it's over 2. Yeah, sine squared theta. No, that's not going to help me. Sine squared, there you go. Is that going to help me? Sine squared 2 theta 1. Yeah, okay, that is what I was going to say. Yeah, okay. Thank you. So someone sent me it. So I'm going to rewrite this. I have it there on the board, actually. Now I see it. So I'm going to use the identity here, which is that cos 2 theta equals 1 minus 2 sine squared theta. Okay, but I'm going to rewrite this for sine squared theta, right? So it's going to be 2 sine squared theta equals 1 minus cos 2 theta. Right? Divide this by 2. Divide it by 2. And now I'm just going to change it because I have 2 theta in here. So if this is 2 theta, then this is going to be 4 theta, right? Because 2 times as much. And there we go. That's what we're going to use. So it's going to be 1/2 of 1 minus cos 4 theta, d theta, equals 8 integral 5 pi over 12 pi over 2. But I'm going to take the half out, right? It's going to be 1 minus cos 4 theta d theta. It's going to be 4 times the integral from 5 pi over 12 to pi over 2 of d theta minus 4 times the integral of 5 pi over 12 to pi over 2 of cos 4 theta d theta, which is going to be 4 theta evaluated from 5 pi over 12 to pi over 2 minus 4. Integral of cos is sine, but it's going to be 1 over 4 sine 4 theta evaluated from 5 pi over 12 to pi over 2. Okay, and so we get 4 times pi over 2 minus 5 pi over 12 minus 1, so minus sine, okay, 4, so it's going to be sine 2 pi minus sine of 5 pi over 3. Okay, So this is going to be 6 pi over 12. So this is going to be 4 pi over 12. No, 4 times 4 pi over 12. No, 1 pi over 12. Yeah. 12 minus sine of 2 pi is 0. So minus, just write that's 0. And sine of 5 pi over 3, I don't know what that is. Let's take a look what it is. Sine of 5 pi over 3 is negative root 3 over 2. So it's going to be positive root 3 over 2. So I'm going to get pi over 3 minus root 3 over 2. Okay, so that is that area there. And I think for the sake of time, because we only got about 4 minutes left, for the sake of time, I'll just say, okay, that area is equal, because it is equal, right? We can see that it is going to be equal. And so this equals S1, but it also equals S3. So our final answer, our area, is 4 times S1 plus S2 plus S3, right? Which is going to be 4 times pi over 3. Well, sorry, 4 times 2, just call it S, 2S plus S2, which is going to be 8S plus 4S2. Okay, so that's going to be 8 pi over 3 minus 4 root 3 plus 4 times this right here. So 4 times 2 pi over 3, which is just 8 pi over 3. Okay, and then this is going to just turn into 16 pi over 3 minus 4. That doesn't simplify. No, common factors. Okay, there we go. And that's our final area for that question. I'm pretty sure that's right. Let's make sure. Yeah.
Yeah. Adam,
Yes.
to interpret that, would you think that the minus 4 root 3 is like the sides, like before the coordinate planes, like the x-axis and the y-axis? Like, why would there be a negative 4 root 3? It's just a theory.
Yeah, why? What are we subtracting just by looking at this? What are we subtracting? I guess what we're subtracting, well, I have to see what's 4 pi root 3. So 16 pi over 3 is 8 times as big as this sector. So you take this sector and multiply it by 8, right? The S2, you take S2 and multiply by 8. And from, why did it multiply by 8? What? S2, 8, or S2. Oh yeah, that makes sense. Yeah. You take that sector and multiply by 8. And then the correction, I guess, is to subtract 4 root 3. I don't know. I don't know how else to interpret it other than that. Yeah.
Okay.
Adam,
Yes.
on the practice test, and I don't think that this was something that was covered in class, but I was wondering if it would be applicable here. There was a question that asked to, given a function, determine whether or not it was symmetric, a polar function, let me specify, whether or not it was symmetric about the origin, symmetric about the y-axis and the x-axis. Would we be able to apply that here to prove that S1 is equal to S3?
Oh,
And if
to
so,
apply
like,
that, yeah.
was that something that was covered, and did I just miss it?
I'm gonna be honest. I don't really listen that well to the lectures, so I'm not sure if he covered it. I think he did, but I definitely put it in my notes. So here are all the rules to figure it out. Oh, it's not copying over. There it is. So here are all the rules of it. So symmetry about the polar axis, either of these cases, if either of them are true. They don't both have to be true. Both of these are tests. If one of them are true, then it's symmetrical about the polar axis. Oh, I misspelled symmetry. I'll fix that. And then you have the symmetry about the pole, and then again, two separate tests. If either one of them are true, then you are symmetrical about the pole, and then symmetry across the y-axis.
And the pole is the origin, right?
Pole is the origin, yeah.
Okay.
I'll fix that typo. But anyways, yeah, there we go.
Wait, I have a question.
Yes.
Actually, I have two.
Yes.
So you know how Kim does the point plotting method, right? Are we supposed to do that tomorrow in the exam?
Possibly. I don't know if he's gonna give a question that's just like plot this. They're relatively, yeah, you know, it takes some practice to be able to plot them, right? But it's just always just imagine you have this sort of like ray coming out. It's really good to imagine rays. Oh, this is something I forgot to mention. I was gonna, you know, before everybody leaves, I have a thing that I made a little while ago, and it's this little polar function plotter. I think it's a really good way to visualize polar functions. So if I just do like this and I just increase the scale a little bit, it's a really good way to imagine how this graph is plotted. So that's what the final graph is going to look like. But a really good way to imagine how it's plotted is to imagine the sort of ray that's tracing it out, which is exactly how we do parametric equations, right? Or vector value functions. So you just imagine this ray that's kind of going out and plotting it like that, and then imagine as the range is increasing, you want to connect the dots, and it's drawing this little shape here. I decided to program this because I never see any visualizations online that actually do it. And as you can see, as you increase the range more and more and more, it just starts repeating on itself. But what's happening, I'm going to go backwards now, is you're just telling this ray to trace out this shape. So I got a couple here. Got this one too. Bring that out a little bit. Increase the range. So you see, again, it's just the ray tracing it out. And so the ray is defined by some sort of length given some sort of angle. So as the angle increases, the length of the ray is changing as a function of that angle. And so hopefully this might help out visualizing.
Sorry, Adam, you made this, right?
Yeah.
Awesome. How long did it take?
I can't really remember. I made it at the beginning of the summer. So I can't remember at this point, but it was like a day or two to make. Something like that. Yeah, it took me a day.
All right.
And so we have this, and then we just again, just imagine plotting it out like that. This one's not right. It doesn't graph it properly. That's not what the function looks like. Still think it kind of looks cool, but and then this one's kind of cool. This is a polar function. The polar function, I wrote them here. 5 plus sine 7 over theta. Kind of a cool looking one. So if you imagine theta going across, see theta has a bunch of jumps right there, right? But then as if I set theta to the max and then increase the range, right, it just turns into the circle kind of thing. Anyways, just thought I'd show that here before I go this here. Oh, okay. Thanks for the support, everybody. I didn't even see that. Let me just see what everybody's saying. So what program did I use? I only really know how to make things in Game Maker Studio. So Game Maker Studio is what I made this in. Yeah. Would I make it in? Yeah. Oh, you're gonna post a link to this recording in the Discord. Yes, I will post a link to the recording in the Discord. And okay, and yeah, if you want a piecewise question. I mean, that's pretty much it. So if anybody, if you want to just send me a question after, we can talk about that. We can talk about that after for sure. But that's pretty much our time for today in this session because that's our. I said I have 2 polar ones to start. Yeah, you're right. I did say I have 2 polar ones, but we did run out of time. So the other polar one, actually it's parametric. Oh, you know what? Before we end it, I have one last thing to show you. It's just how you would solve this question. And I'm just going to show you how to graph parametric things. Okay, that's the last thing. I'll just show you how to graph parametric equations. So this is the one, 101. It's actually not polar, sorry, it's parametric. And so the way I graph parametric equations is in GeoGebra. So we won't go through the full solution for this one, but GeoGebra is here. So GeoGebra is better for this. And I'm just going to show you how I graph it. So it's cos t e to the t. The range is 0 to pi over 2, right? So this is how I do it. You type in the word curve. Okay. Hit enter. You start typing cos t. Okay. The next expression is e to the t. The next thing it wants is the variable t. Start value 0. End value pi over 2. There we go. I plotted a parametric curve. And now the integral of this parametric curve. Now the particular question is saying that we find the area bounded by the curve and y equals 1, x equals 0. So let me plot that here. Y equals 1, x equals 0 is this right here. So we're really looking for that area. And so the way you do it is you just use the formula to integrate this. Right? You just use the formula. Let's find the formula here. So we're looking for parametric integration. So let me just find that here. Parametric integration. Okay. So you use just the basic formula for parametric integration, which is this. Whoops, I don't want it twice. Oh, it's freezing on me. It's freezing on me. No, it's just gonna stay there. No, it's just gonna stay on my middle of my screen. Okay. Let me just open this up.
I think it's because you still have like the Fourier series thing running on Desmos still.
Oh yeah, you think possibly that could be screwing with me here? I'll remove it. See if that does anything. Drag and drop. Oh, it thinks I'm still dragging dropping an image. Oh, okay, interesting. Even here, I think I'm still dragging dropping an image. Okay, can I do anything here? There we go. Now it stopped. There we go. So you just do the parametric integration here of this curve. Let's do it. Whatever. But you know, it won't take. So to find that area, it's going to be the integral from 0 to pi over 2 of y of t. So y of t is just e to the t. X prime of t is just going to be negative sine t dt. Okay. I'll just plug I mean, this is integration by parts twice, right? That's what this is, integration by parts twice. You do that method where you bring it to the other side and then divide by 2 and all that. So I'll just use the calculator quickly for this, just to save a little bit of time. So it's going to be fulcrum, I guess. So it's going to be here, integral from 0 to pi over 2 negative e to the t sine t t. So this integral is going to be so it's going to be 1/2 1/2 negative 1 minus e to the pi over 2. That's what that's equal to. But you have to remember that that area that they just gave here is that where's GeoGebra? Is it? Where did it go? There it is. That area that we just calculated is this. Come on. Let's see. There we go. Is this entire area past that bottom line. And so what you got to do is you got to subtract off this area. But that's just a 1 by 1 square. So we just subtract off 1. And there we go. That's the answer for that one. It doesn't match the textbook answer, but the textbook answer is wrong. I did this. I went through this for a long time. The textbook answer is wrong.
Wait, sorry. You're saying that you've found the area, but the area is actually from.
So the integral gives me this whole thing.
Okay.
But what I want is this area.
Yeah. Can I see the integral again?
The integral, yeah.
Okay. Is it similar to the coordinate thing that we were just doing with we have 0 to 2 pi over 2? Did you say the calculus was wrong? That's what he's.
I'm saying the textbook was wrong about the answer to this question. Right. Yeah, that's it. So the bounds are just given to us.
Oh, okay.
0 to pi over 2. That's all it is. It's not even a polar graph. It's just a t value that varies. The bounds are just given to us. And then I just have to account for the fact that there's this 1 by 1 square, which is part of the integral, but not part of the question. So I just got to subtract 1 off there.
But how did you know that it's not a part of the? How did you know that the integral they gave you also includes a 1 by 1 square?
Because the integral of a parametric curve gives you the area between the curve and the x-axis.
Yeah, you're right.
Right. So, but if I'm bounding it like with that line there, right? If I have an extra bound, I have to subtract off that area.
Yeah.
Right.
You're right.
Subtract that off. Okay. And now that's all our questions. So I'm here for a few more minutes to answer any questions people have, but that's all the content I'm going to cover. Hopefully that was helpful for everybody. Nice review of everything. Hopefully everything makes some good sense. And have a good night. Good luck on the test. Hope everything goes well. And again, I'm just here for a little bit to answer people's questions. No problem, guys. No problem, guys.
I have another question.
Yeah, for sure.
If you do decide to use point plotting on the exam, right? Do you have to include the negative R's that you get? Because Kim didn't include those, but when you graph them on Desmos or even in the textbook, they include the negatives.
Yeah, you do include the negatives. So essentially you just say it's at an angle, but the negative goes the opposite, it's going the opposite way, right? So you draw a temporary little ray. So if you had if it was R is negative 2 whatever pi over 2, right? Then that's going to be a ray like this, right? Because with a length of 2. Because that angle is pi over 2, but the length is negative. So we go down.
But we shouldn't do that on the test, right?
We should or shouldn't?
Should not, because like he said to just whenever you have a R value that's negative, you just completely disregard it,
Just
correct?
discredit it? Yeah, if that's what he said, then yes. If that's what he said.
Okay.
Then he won't give questions that, hopefully he won't give questions that will change that. No problem.
Wait, but
everybody.
doesn't that change the question itself? Because if you're, I think it was 209 that we just did. It does have like negative R's, but when you plot them, like when you disregard the negative R's, you only have the pedal in the first quadrant and the third quadrant. You don't have any in the second and fourth.
First quadrant and second quadrant. Yeah, I have run into issues with that. I don't know if I have a good answer of how to deal with it really. I have run into issues with that before. I remember during practice. Yeah, I remember exactly that specific thing. That it's like we had like only 2 pedals instead of the 4. Yeah, I'm not sure. I think I'm not sure. I think doing with the negative R values makes more sense. But again, if he said not to do that, then that does cause some sort of complications. So I'm not really sure.
It's kind of confusing because like in the practice test, there's a question with where it asks you to like find the area in the inner loop of whatever function they give you. And for there to be an inner loop, it has to like the negative R has to be accounted for.
Accounted for, yeah, exactly. And it should be accounted for because that's part of the graph. Maybe he meant don't include it in just a sketch. No, but then you still need to see it somehow. Yeah, I'm not sure. I'm not sure. Not too sure.
Sorry, Adam. So I just want to add on. So there was still one more topic that's also going to be on the exam. I forgot what it's called, but you know how there's like different domains. It's the one with the theta and then I forgot what it's called. You know how there's 3 coordinate systems?
Yeah,
forgot what the
like
other one was.
rectangular, cylindrical, and spherical.
Yeah, spherical. Yeah,
that won't be on the exam.
Oh, it won't be.
It won't be. No.
Okay, because it was on the practice test, so I thought it might be on the.
It was on the practice test, but it is not on the exam.
Okay, cool.
It's not on the midterm. That's 2.7, which is past the bounds. Yeah, he included it by mistake. Okay, someone asked in the chat quickly, why did we use 2 theta when I was finding theta 2? Let me go back up to this question. Went too far. When I was finding theta 2, why did I do pi minus pi over 6? So when I type in my calculator sine inverse of 1/2, right? It gives me. Notice this. This. There. Let me just do this here. Okay, there we go. When I type in sine inverse of 1/2, it's doing it again. Oh my god, sorry. Good that it does it at the end, not in the middle. I bent the cord. I realized that's the problem. I bent the cord by accident, and I don't know if I have another cord. But I mean, it's just a micro USB cable. But anyways, pi over 6. That's what I get. But that is the first solution, right? There's infinitely many solutions. So pi over 6 looks approximately like this, right? But we use our cast rule here. Remember, cast tells us that my next solution for a positive input is going to be in the second quadrant, right? All are positive here, sine is positive here. So I need to move my angle into this quadrant. How do I do that? Well, essentially what I do is I do pi minus the angle. Pi minus the angle. And I move that angle into this quadrant now, right? Pi minus the angle gets me whatever this angle is. Pi minus, so it gets me that. And so my next solution is pi minus the angle. And then the next solution after that is just 2 pi plus this one, and then 2 pi plus this one, and then 4 pi plus this one, and then 4 pi plus this one, and you keep going up like that. Does that make sense? Does that answer the question there, how we did that? Okay. Yes. One person went over your head, and then Joshua, but the person who asked the question says yes, thanks. Yep, I can help.
I just had a quick question about the Fourier series.
Okay.
So let's say you're given a question and it just says calculate the Fourier series, and the function, it's an odd function. So can you just go straight to the Fourier sine series?
Is it defined on negative p to p or 0 to L?
Let's just say negative p to p.
Then you can go right to the sine series.
Okay, and then if it was 0 to L?
Then you have to do the Fourier series.
Okay.
Then you have to do the Fourier series, which is where you choose p to be L over 2. Right? That's the thing here. You choose p to be L over 2.
Oh,
And
okay,
then-
thank you.
right, no problem. I kind of got to get going because I have something at 8:30 and then I need to like eat and stop for a second. But any last questions before I get going? I will stop.
Just to add to that last question,